Good morning, everybody. I would like to welcome you to the tutorial on Scalable Graph Neural Networks with the Deep Graph Library. So the agenda for the day is as follows. So to begin with, we're going to have two presentations. They are PowerPoint presentations. So the first one will be give you guys an overview of graph neural networks, while the second one will be an overview of the Deep Graph Library. After that, it will be a half-an-hour coffee break. And then it will be a hands-on tutorial that is going to cover GNN models for basic graph tasks. After that, it will be a 1 hour lunch break. And then when we come back, we're going to have two hands-on tutorials. One will be on GNN training on large graphs, and the other one on distributed GNN training. So my name is George Karipis, and I'm a senior principal scientist at AWS Deep Learning Science. I'm based out of Palo Alto, California. I'm also a professor at the Department of Computer Science and Engineering at the University of Minnesota. And I'm currently on leave at AWS. You guys can get a hold of me if you want to contact me using either my Amazon email address or my U of M email address. So to motivate the use of graph neural networks, I would like us to consider three applications. Right? So the first application is that of fraud and abuse. And the goal over here is to be able to detect malicious accounts, identify fraudulent financial transactions, fake reviews, fraudulent insurance claims, etc. So the second application is that of recommendations. I guess most of us are aware what the task over here. The goal is to recommend products, media, article experiences, jobs, and so on to individuals. And the third application is that of marketing. And what we want to do over here is to be able to, figure out to whom should I offer a discount, how to identify who are the influencers, so that I can market them directly. And another one may be identify which of my customers are most likely at risk of churning, so I can take some proactive actions to prevent them from doing so. Okay, now, what is common in all of these applications is that they use graphs to represent the underlying data. For instance, in the context of fraud and abuse, if we're talking about financial transactions, usually there is a financial transaction network that is used to represent the relevant information. In the context of recommendations, usually what we have is what's called the collaborative knowledge graph that contains information about users, the different items they interacted, as well as any other information that describe the users, as well as describe the movies, right? So, and in the context of marketing, quite often, what I have access to is some form of a social network. Okay. Now, what's even more interesting is that I can use these graphs to solve the underlying problem by using machine learning approaches based on graph learning. Okay, so I can use those approaches to figure out, which are the entities in my network that corresponds to fraudsters. I can identify, for instance, which movie to recommend to a person, or can identify, which are the most influencing people in a particular social network, so that I can market them directly. So when we talk about graph learning or machine learning on graphs, we usually kind of consider three tasks. So the first task is that of node classification. The second task is that of a link prediction. The third task is that of a graph classification. So now within the node classification, the goal is to be able to predict the class or predict some form of value for each node in the network. And things like detect malicious accounts or target the right customers are instances of node classification tasks. In the context of a link prediction, the idea is to predict a missing link in the network. And that is actually the way I formulate the recommendation problem, because the recommendation problem becomes of predicting a new link, right, between a particular user and a particular item, right? So this is kind of the link that I'm trying to predict. Or another case of a link prediction is that predicting missing relations in the context of knowledge. And in the context of graph classification, the task over there is to be able to predict the class or predict a property of an entire graph. So a prototypical use case for graph classification is in the context of chemical informatics. So in which, what I'm like to be able to do is I would like to be able to predict certain properties for a particular compound. Right? For example, a very important property that a lot of people would like to be able to predict for a compound is whether or not that particular compound, will be able to treat a particular disease, right? So being able to predict that type of property then will help me in the task of drug discovery. One way to solve the various graph learning tasks is to use node embeddings. The idea behind those approaches is to embed the nodes of the graph into a low-dimensional space in such a way so that the embeddings capture the essential task-specific information. Now, once I have those embeddings, I can use those embeddings as inputs to traditional off-the-shelf classifiers, such as neural networks supported by machines or even decision trees, in order to solve the classification task at hand. Now, over the years, there has been a bunch of different methods that have been developed to compute those embeddings. Okay? One class of methods generate those embeddings by doing manual feature engineering. So that requires domain expertise, involves considerable manual fine-tuning, is in general time-consuming and simply does not scale. And there's been another class of methods that have been developed and have become very popular, in which they generate those embeddings automatically using various unsupervised dimensionality reduction approaches. Things like single value decomposition, tensor decomposition, cofactorization, deep walks, etc. are examples of some of those methods. However, the problem with those things is that they cannot effectively combine the attributes that quite often we have with the nodes and edges in the network. And that to a large extent, most of those models are mostly multilinear models. And they decouple the learning of the representation from the downstream classification task. So they do not allow for an end-to-end learning. So which begs the question, can we do better? Okay, and the answer to that question is graph neural networks, right? Graph neural network is a family of deep neural networks that learn node, edge, and graph embeddings. So the way graph neural network works is as follows. So we have a graph over here, and there's a particular node over here, let's call it target node, for which you would like to be able to compute these embeddings. So what the graph neural network does, it looks at an ego network around that node. And the ego network is a network that is centered on that node that contains all the nodes that they're up to k hops away from that target node. So once that ego network has been identified, okay, then it learns functions to compute the embeddings of the target node by taking into account information about the structure of each ego network, as well as the attributes of the different nodes and edges involved in that ego network. And that embedding that is computed for that node, right, is learned in an end-to-end fashion, based on the downstream classification task. Okay. So graph neural networks were introduced, around 2014. I think some of the early papers around the time frame, and they have become extremely popular. I mean, this is a chart that obviously is dated by a couple of years, but the number just has is increasing at an exponential rate. So there's a lot of research on graph neural networks and a lot of excitement. And the primary reason for the excitement is that what graph neural networks allow they bring the power of deep neural networks on relational data, right? And quite often in most applications, relational data is significantly more predominant than non-relational data, things like images, text, video, and so forth. So really, it's just a way by which the advances in deep learning can permeate to many different domains. So another advantage that the graph neural networks have is that they keep being trained together with a downstream task in an end-to-end fashion. And as a result, they can learn representations that they are very well suited for the classification task or link prediction task at hand. To give the idea about why the thing is happening is how the thing is happening is in the traditional method. What I have, given a graph, I use a traditional method of computer embeddings. When those embeddings are computed, then what I do is I use them as inputs to a classifier, in order to solve, let's say in this particular case, a classification task. Now, during this training of the classifier, right? So the gradients, propagate in this classifier's model parameters, and I will never get that supervision signal to actually go and change the embeddings, right? So I never have gradients, propagate all the way back into that model over here that computes, the embeddings of the nodes in the graph. On the other hand, in a GNN, what I have is I go from the graph, I apply my GNN models, I get the embeddings, I take those embeddings as inputs to another model that will give me the classification, and I use that model over here to predict the classes, right? And then when I backpropagate both on the model parameters for the classifier as well as the model parameters for the GNN. So what that thing allows me to do, it allows me to actually train the GNN to compute embeddings in such a way so that those embeddings are well suited for this classifier in order to perform really well on this classification task, right? So, you can imagine that leads to much better performance than the traditional approach in which, those two things are not trained in an end-to-end fashion. And the final reason that why graph neural networks are better is because the fact that graph neural networks are inductive models because they learn the same neural network on all the nodes and edges in the graph. So remember from the picture that I have shown to you guys earlier. So what GNNs do is that they learn a function to compute node embeddings from the features of the node's ego networks. Okay? When those features do not encode information about the identity of the node itself, but correspond to features describing attributes and characteristics of those nodes, then those functions can be applied to any ego network to compute the representation of the target node. Okay, so remember what I said, So, and as a result, what I can do with that is that I can train a model, right, on some graphs, right? So I can use that model to learn how to compute a representation, let's say, of an individual, right? And I can do that thing in an end-to-end fashion. And once the GNN model has been trained, then when a new individual comes into my network, that individual was not there when I was training the model, but that individual does connect in the network. So there is an ego network that can derive from the individual. Then I can apply that model that I have already computed to actually compute an embedding, right? So you can think of a GNN as a computable embedding. So as opposed to the traditional methods that they learn an actual embedding, what GNNs learn, they learn functions that on how to compute those embeddings. Okay, so as you can see, that allows them to train to do really well for cold start settings, right? Allows them to train the model on a subset of the graph, and then apply the model on another part of the graph or an entirely different graph to actually compute embeddings, and so on. Now, so one of the things that, as I mentioned earlier, the reason that thing works is because the model that they learn, right, they take advantage of the features that describe the attributes or characteristics of the nodes in the graph. Now, quite often, sometimes, we do not have such features, and what commonly is done is to do a one-hot encoding of the nodes in the graph, right? Once I do a one-hot encoding of the nodes in the graph, at that point in time, that inductive bias is lost, right? Because I have encoded in my function information about which were the nodes involved in learning that function, right? So that differentiates what's called the inductive versus the transductive models, GNN models. Okay, so now that you guys have some high-level idea about, what are GNNs and, what are the problems that they're solving and how they work and what they're good for. Okay, I would like you guys to give you some example of some, classical by now, GNN models. So the very first model I would like to briefly describe is the graph convolution network, right? So this is kind of a graph equivalent of a convolution network for images. Okay, so in that network, the message passing function is nothing more as communicating a node's current embedding, scaled by the degree of node V, right? So the aggregation function is nothing more than the summation of those messages that were received. And the update function takes that aggregated message, multiplied by a weight matrix W, and then applies a nonlinear activation function to update the representation of the node, right? So pictorially, so given an input graph like that, then during each layer of the GNN, what happens for every node, it receives the representations for every node over here. It first aggregates the representations of each neighbors, so through over here. And again, that aggregation is involves the neighboring nodes, right, as well as the representation of the node itself, right? So it adds those things up, and then it divides everything by the degree of the node V plus 1, right? So remember, the degree of the node V in this particular case it will be 3 plus 1. So the end result of that part is nothing more than the average, right, of the embeddings of each neighbors plus itself. Okay, and then it takes that representation and then multiplies by a dense matrix, weight matrix, right? And then does a pointwise, nonlinear activation, right? So in this particular case, the function I will use is, for instance, a value in this picture. So this is one hidden layer. Then this is one layer of the GNN. Then I can do the thing one more time. So again, this time now I'll be averaging the averages of the previous iteration, right? And I can do that thing multiple times. And each of those things will define a layer of the GNN, of the GCN. And then at the end, I'm going to get, for every node, the final representation of the nodes, going through that process. Okay, so again, this is a very simple network. So the only model parameter over here is that weight matrix. And this is the weight matrix in which on how the representation of the new representation of the node, right, will be computed as a function of the average of the representations of all of its incident nodes plus itself. So an improvement or a generalization of that model is, instead of just doing an unweighted average, to do some form of a weighted average and determine the weight by using an attention mechanism. So that gives rise to the graph attention network. So the idea here is, again, so I have the message corresponds to nothing more than the representation of a node at the previous level. Now, instead of divided by the degree, I have some activation weight, some attention weight, sorry. So then I take those messages and just aggregate them. And then I pass that aggregated message multiplied by weight matrix and then through a nonlinear activation function, right? And the way I compute the attention weights is using a standard, softmax approach, in which I have the embeddings of the source and destination of the two endpoints of the edge, right? And I first, project them using a matrix W, concatenate those things, and then learn a parameter alpha that will give me the dot product. And then, using a softmax, I compute those attention weights. Another classical GNN is the relational graph convolution network. So this, in most real world settings, the graph on which I need to operate is actually a heterogeneous graph consisting of nodes of different types. And those different types nodes are connected of relations of different types. So what IGCN is designed to do is designed to generalize GCN, the graph convolutional network, in such a way so that it will take into account those different relation types. And the way the thing is done is as follows. So what I have is and the best way to think of it is something like that, right? So so again, I have messages being sent, right? So the way that those messages are sent, instead of just copying the representation, just sending the representation of a node, right? Each node multiplies its representation by dense weight matrix, and the dense weight matrix is relation type specific, right? So that corresponds to the message. Now those messages are aggregated, right? And then that aggregated message is used to update the representation of the target node by first multiplied by weight matrix and then applying a nonlinear activation function, right? So the key difference between the way the different relation types are handled in the relational graph convolutional network is by having those relation type specific weight matrix, right? That is used to generate the message to be sent to the target node, okay? So I'd like us now to switch gears and spend a few slides to talk about how to train GNNs in end-to-end fashion. So remember that an L-layer GNN, what it does is it computes a representation for each node in the graph, right? And then each of those, then this representation is fed into a downstream model, which is often an MLP, to compute a prediction. A loss function is defined, and gradients are backpropagated all the way, to the MLP model parameters as well as the GNN model parameters, right? So this is the picture that we saw earlier over there, right? So I apply the L-layer GNN that is over here to compute the representations. That classifier over here, then the representation fed to a classifier, to a model, and that is using MLP. Something gets computed over here, the prediction is computed, the loss function is defined, and then then the gradients are computed and backpropagated all the way out to both the model parameter for the classifier as well as the model parameter for the GNN. To make the thing more concrete, let's look at the problem of node classification. So in this case, what I have a bunch of nodes in the graphs. Now for some of those nodes, I know they're labeled. Now for some of the other nodes, I will not know for their label. For the ones that I know they're labeled, I will compute their representations. And then I take those representations usually through an MLP and then define a loss and backpropagate, right? So a typical loss defined is a cross-entropy loss. And this is, how something like that will work. So recall from the previous notation, H sub V superscript L is the representation of node V after L layers of a GNN. Then W over here are the parameters of the MLP, and label is the actual ground truth label for that particular node. And then I define a cross-entropy loss, and using that I will do backpropagation. So remember I mentioned over here in a semi-supervised setting, so quite often when I want to do node classification, only a subset of the nodes in the graphs will have labels. It's only for those labels for which I define the cross-entropy loss, and I ignore the rest of the nodes. Now, the rest of the nodes and their features are used while I compute the embeddings of the nodes with labels, but they're ignored when I define the cross-entropy. Okay, so in order to supervise link prediction, we first create a loss function that rewards the pairs of vertices that are connected via edges. Now, those edges are usually called the positive edges. And at the same time, it penalizes the pair of vertices that they are not. Usually those called the negative edges. Okay, so we have the loss function that rewards the positive edges and penalizes the negative edges. Now, in order to be able to compute that reward, right, to measure that reward, what we usually do is we define a function whose score should be high if a pair of vertices are connected via an edge, otherwise it would be low. Okay, and a common function that people use to compute that score is the sigmoid of the dot product between the GNN derived representations of the two nodes involved. Okay. So now let's make that thing a little bit more concrete, right? So so my goal is to score the presence of the edge between 1 and 9, right? So what I do is I use a GNN to compute a representation of node 1. I get the GNN to compute a representation of node 9, right? And then I have a score function, which is that is the dot product of those two representations, that the HV will correspond to 1 and the HW will correspond to 9, for example. Right? And attach that into a sigmoid function. So this is a function that measures, right, that should be high, right, if there's a real edge between 1 and 9, and should be low if there's no edge between 1 and 9. Okay, so now given that we have now defined all the different pieces, now that the loss function, what we do is usually, for every positive edge that we have, right? So we generate a set of negative edges, and the way that we generate those negative edges is by, randomly sampling a pairs of vertices, right? That they're not connected via edges, right? And then for both the nodes involved in the positive edges and the nodes involved in the negative edges, right? So we compute their GNN-based embeddings, right? They compute the associated dot products and the sigmoid of the dot product using that, and then we optimize the loss function, that's defined over here, right? Which it encourages that the edges, the positive edges to have a high score, and the negative edges to have a low score. Okay, and again, so this is the end-to-end loss function. So you can think over here when I do propagate gradients, those propagating gradients go through those embeddings, of HV and HW, right? And similar over here, and those embeddings will will be computed, the output of the GNNs, so that will also backpropagate the gradients to the GNN model parameters. Finally, for the graph classification problem, so this is somewhat different than the node classification and the link prediction, right? Because what GNN does is used to compute embeddings for the nodes. In the case of the class classification, what I would like to do is I would like to be able to predict something from the entire graph. So in that case, what I do first is I do a readout of all the embeddings of the graph, right, into a single representation. So I have some sort of a readout function, right, and that can be potentially a trainable function. Okay, and then once I have a single vector representing the graph, right, then I can usually use a cross entropy loss. I have its own weight metrics, or that can be potentially an MLP, right, to define the loss, and then backpropagate from that loss to G, and then from G through the individual representations of the nodes, and then from those representations of the nodes to the GNN model parameters. Okay, so finally, the last part I would like to cover is how to train very large GNNs. Okay, And there are many applications out there for which we need to train GNNs on a very large graphs. Some of those graphs can easily contain millions of nodes and billions of edges, right? And quite often those large graphs arise in settings in which the model is sometimes transactive in nature, even though I may still have inductive large graph training problems. Okay, some of the domains in which those things arise, like social networks, you would like to be able to compute embeddings for individuals in very large networks, and the recommendation setting computing embeddings of millions of products and millions of users, as well as in a very large knowledge graph. Okay, so one of the challenges in training very large neural networks is if I want to be able to take into account, take advantage of accelerators such as GPUs, then for very large graph, it's simply not feasible for me to load all the data into the GPU memory, right? So in order to be able to do that, then I have to actually break the graph into smaller chunks, and a typical way of doing that is by employing some mini batch training. So the idea of a mini batch training is as follows. So remember that that in a GNN, what we do is we compute representations of nodes, right? And those things are supervised in an end-to-end fashion, right? And to a large extent, the individual training datum in a GNN is that of a node, that usually refer to that thing of a target node, right? So I can create a mini batch of size 1, right? That has a single target node, right? By just extracting its ego network. Okay, so this is a mini batch of size 1. And if I want to have a mini batch that is larger than size 1, then I will usually select a subset, like a small number of target nodes, right? And I compute the ego networks, and the union of that will define my mini batch. So I mean, this is a reasonable way to control the complexity of the problem, to reduce the complexity of the problem. However, the caveat with that approach is most real-world graphs, they tend to have a power law degree distribution, right, or correspond to the small world graphs. As a result, what can happen is even if I focus on a single target node, right, and I expand an ego network that is 2, 3, 4 hops deep, right, that can easily include an extremely large number of nodes, right? Especially if I hit some of the high degree nodes in my graph, okay? So that my initial goal of creating a mini batch such that its memory footprint would be reduced, so I can be able to leverage GPUs for high computational performance cannot really be achieved. So in order to deal with that, most mini batch based training algorithm for GNNs, in addition to creating a mini batch by focusing on a small number of target nodes, they also employ various neighbor sampling approaches to reduce the size of the ego networks, right? So the simplest neighbor sampling approach is a degree-based, is a neighbor sampling based on a maximum degree. So for instance, I can put a bound that will say that for every node, I'm going to only sample up to 2, no more than 2 of its neighbors, right? So then in that case, I can guarantee that the maximum size of the ego network associated with a particular target node is bounded by the maximum degree raised to the depth of the network, right? So this is the case in which I have a neighbor sampling which I put a bound of 2 on the degree of the maximum degree of the nodes that I will, the maximum number of neighbors that I will be sampling. Okay, so But again, this is just one of the sampling strategies. There are a number of different sampling strategies have been developed, right? And but the primary design goal for those sampling strategies is to be able to deal with the fact that without sampling, I can potentially run into some serious, computational problems and memory problems. So finally, to summarize, so there are a lot of problems, right, that can be solved by formulating as graph learning problems. And for this class of problem, the graph neural networks represent probably the current state-of-the-art technique for solving them. They have a number of advantages over traditional approaches. And because of these advantages, right, it's has become both a very exciting area of research, and also GNNs are increasingly find their way into a wide range of production applications. And I personally expect that number to continue to grow. Well, thank you very much.